Hi, I'm Dr. Christopher Newman. I'm Professor of Space Law and Policy at the University of Northumbria in Newcastle in the United Kingdom. I'm also International Space Law Advisor for Cold Star Technologies. I listen to the Cold Star Project.
This show is for entertainment purposes only and is not what is termed professional advice. The Cold Star Project is proudly presented by the Operational Excellence Society. Cold Star Tech is a supporter of the OPEX Society, and Jason Kanigan is a member of its board of advisors. Talk with us at Cold Star Tech to find out what we can achieve together with your Lean Six Sigma or Operational Excellence programs. And check out opexsociety.org to learn more. All right, let me remind you before we get into this episode that Cold Star Technologies is a promotional partner with the America's Future Series, a national security and space and military technology platform for discussion. So check that out. We have events ongoing all the time, always upcoming, great speakers, military technology speakers, America's Future Series. All right, my guest today is Dr. Jacob Meyer. He is the Vice President of Technology at ATSP Innovations. And what that stands for is aromatic thermosetting polyesters, okay? And this is a new type of coating. And the reason I wanted Jacob on is because he's been through that SBIR process, the SBIR Level 1, Level 2 process, and is driving towards having a commercialized product here, which is very important in the space industry. A lot of our products, they kind of get bought on spec and put into the vault, and that's not great. Usage, user adoption, use cases, this is really what we want. We want people using these things and making money with these technologies in space, or else space is going to remain the domain of the military, and us commercial B2B guys are never going to get at it. All right, so I wanted Jacob on to talk about his experience with the SBIR process, what worked well, what was a challenge, and so that we could learn from it in driving towards having an actual commercial product out the other side. So Jacob, welcome. All right, so let's begin with this then. You're thinking about doing an SBIR, you have a technology in mind. What problem were you trying to solve?
So with one of the original SBIRs that we ever did was basically NASA was asking for a adhesive that could work in space and would provide such and such amount of strength, and would also be reversible, as you could break it and then do something with it and put it back together. What they were originally asking for was something based on what's called a gecko adhesive, which is basically the audience can go Google it, but basically it's typically a surface with lots of these little, bio-inspired fibrils on the surface there that offer adhesion based on some of electrostatics plus van der Waals plus basically the vacuum pressure from the other side. Okay. Well, without basically the air pressure from the other side in space, that number is going to be a little bit lower than even usual. But what we offered was something based on our technology, which is in concept called a vitromer, right? So the idea that we had, right, was what if instead of basically something that was a rather weaker bond, that you could do the same thing in a smaller area with a much stronger covalent bond that was still reversible. And we managed to do this during the proposal preparation phase, we quickly put together some little proof of principle experiments. We put those in the proposal, and we won that proposal, right? Everyone always feels good when that happens, of course. Right. It feels a lot better than losing, which we've lost plenty of course. But the basic idea of a vitromer, which is a type of polymer. So typically for polymer chemistry, or when you're talking about polymers, there's really two types that people use industrially, and that's linear polymers, which are typically called thermoplastics, and then there's cross-linked polymers, which are also called thermosets. A vitromer is a thermoset that, by virtue of its bonds exchanging, can function in many ways like a thermoplastic. And it's called a vitromer because the guy who came up with that term made an analogy to glass, right? Okay. Glass is an inorganic thermoset, right? And at elevated temperatures, right, you can work it. And then at further elevated temperatures, it's a liquid, basically, and you can draw fibers into it. Yeah, you draw it into fibers. And same thing applies with vitrimers. Now there's some limits because this is organic chemistry, and at a certain point it'll just fry, and there's nothing anyone, or like I included, can ever do about that, right? Whereas like glass, like it really doesn't. It's pretty stable up to a completely ridiculous conditions. But we can still work it, we can still join with it, we can break it, we can rebond it, we can remold it, and we can recycle it pretty effectively, just based on those principles that basically, like, the bonds exchange. And at elevated temperatures, they go back and forth. They don't know the interfaces there. Like, it kind of, if people are in this audience are familiar with basically like vacuum welding, like for stainless steels, when you have like basically stainless steel screws under vacuum, a lot of times they'll kind of mesh with each other. A lot of the same phenomenology there, except this is a little bit more controllable. So that's basically the technology we were offering. And so part of our demonstration for that was they asked to basically, like, can you bond and break this over 50 cycles? The answer was yes. And so we ended up winning the phase 2. But the overall idea was, you have all these big structures you want to build in space, and how are you putting those together? And the idea that they were looking for was, is there a simple way to just basically kind of glue these together in space without it being a liquid or anything that's going to be a mess like that? Because I mean, anything that's a liquid in space is going to off gas like crazy, and that's its own set of problems, of course. And it's also just going to be tough to handle because it's going to ball up real quick, right? And so instead, like, what if it was just a solid the whole time? And it's formally a solid throughout this entire process, and it doesn't sag during the bonding operation. It doesn't do anything. It's stable indefinitely, because the polymer is already a thermoset. It's already fully cured. It's basically like a 2-part epoxy, and you've already set it, but at an elevated temperature, you still get to do stuff with it. So that's a lot of the core idea with it. So in order to build these big structures, like, the idea is basically you have like whatever sort of, there's kind of 2 concepts we usually talk about here. One is building trusses. Like you have like basically you want to like either snap something into place or like assemble something piecewise, and you have basically your adhesive layer. You put these things together, you zap it, and you can just keep on extending it out. Or you have some big arbitrary structure, and at some later date in the future, you get changing mission goals, changing political goals, changing business goals, whatever, and you want to put something else on the outside of that thing. Well, how do you do that without basically pre-planned mounting points, right? And oftentimes they'll have pre-planned mounting points, but I mean, sometimes they don't. And what if you could just basically put it really anywhere on the whole thing, and all you had to do was basically just have the structure coated with, or like little points on it coated with the polymer. Those could be your pre-planned mounting points, for example. So you bring those 2 things together, you zap it with, we can use induction, microwave, IR. There's a lot of different options that we've looked at, embedded heating. All of those work, and they're pretty easy to do, really. So we've been able to do all of those and kind of demonstrate it across a pretty wide range of different joint concepts. And that's basically the actual original idea behind one of our first SBIRs here. And that really had a lot of to us a lot of impact on the company, as it really allowed us to basically launch a new product line basically entirely. Like basically that adhesive function was very exciting to us. Yeah.
All right. Yeah, everyone needs this kind of glue.
Yeah, and I completely agree.
Stable. Okay, so regarding the SBIR, the process, what worked well for you?
For the process, actually, one thing I would say that actually works pretty well, but that I'd comment that needs some improvement, is actually just the application interface itself. Like for some of the government agencies, they have a really nice streamlined interface that you just put all your different numbers in, you put your PDF in, it works pretty well in terms of like how to do that. There's a couple of spots where I'd say basically it makes you enter information kind of redundantly, that I think should be polished up a little bit. But other than that, I'd say that aspect of it, that mechanical aspect of it, worked pretty well. In terms of the actual process of putting those together, we ended up basically, one of the ways that we approach this is we see these solicitations, we kind of know what we as a company can do, and then we just kind of look at some of these, and if it looks like it's something we know how to do, it's something we already like. I mean, first off, is it something we've already proposed before, right? Those are always the ones that you want to try again, right? If it's something that you just missed that time, that you want to try it again. You come back with a better proposal, and so on and so forth. Number two is basically, is it something we already know how to do, that we just haven't had money to develop yet?
Okay.
And number three is, is it something we know how to do, but didn't know that anyone was asking for, right? Like, it's like, do we read it and say, oh yeah, here's how you do this? And we've done a couple that are like that, that, we've seen that weren't part of our core business, but that we saw it and we realized we knew how to, or at least we thought we knew how to do, right? Because just because if you propose something at TRL 1, it's not necessarily the case that you're right about that, right? Like, and there is one that we did that we were wrong about. Like, it's not how that this just does not work that way, right? Like, and like basically, like what we've ran into is, I think, basically a limitation on what chemistry can do for us in some cases. You know what I mean? And then on another where we proposed at TRL 1, it worked. It worked right away in a lot of ways. So I mean, it just depends on exactly what you're looking at, right? So when we go from that to basically the actual preparation process, right? That is, we tend to use we tend to, like, and again, mechanically, we tend to use Google Docs for this because to me, that allows us to collaborate most effectively. Like, I mean, we don't have to be trading Word documents around. I just think that's actually a great way to collaborate. And it lets everyone see exactly where the progress is and so on. In terms of, like, basically, so, you get to basically the day you're wanting to submit all this stuff. And someone just has to sit there and hit all these buttons. And one thing I'd like is basically if some of these were a little bit less redundant. Then you get your sitting and waiting, basically while you just to hear if you win. And you win, and like at that point, you got to start like really finding commercial users, hopefully, like in addition to the federal entity that's looking for this. Like, because I typically, especially for us as a materials entity, there's just like, I mean, typically most federal things are not going to have sufficient draw for a material that you can support your business on just that one application. That's not, and they're like, the program managers you're talking to, they're always cognizant of this, right? Like, they always understand that basically we're not going to buy enough to support your business, right? Like, we want this to be on the market and for you to sell it to, whoever commercial vendors, commercial users that can actually take advantage of this technology. And we just want to buy it when we need it. I mean, that's typically their perspective when they're talking to a materials company. Like, that's the expectation. And it's been that expectation in basically every case I've ran into. They always want it to just be something off the shelf that they can select. They want to see basically like a whole portfolio of data related to it so that they don't have to do a lot of redevelopment at some point in the future when they come up with like basically whatever actual mission, right? I mean, that's typically what I've ended up seeing from like materials companies. I mean, as a materials company, what I've seen, coming from NASA is basically, please support it with just regular terrestrial commercial sales. If you see basically, on orbit commercial like opportunities, excellent. It's not expected that we're able to, for a material, to be able to support ourselves with that just on those bases though. It's more like intended to be supported with like commercial stuff on Earth, but this is basically, we do need this development. We do need this material, right? So that's basically what I typically see from them. So there's usually a lot of encouragement to connect with, to connect it with basically like different, more prosaic applications. Like, can it fit here? Can it fit there? Not typically the focus, but like, there's encouragement and like suggestions along the way, like every single time.
Yeah. What kind of reporting requirements does the SBIR process have once you've won and they've given you the money?
So that varies from agency to agency. There's agencies where I've seen like a monthly reporting requirement. So and that's fine. Like and most of the time it seems like it's quarterly. Like even or yeah, it seems like it's quarterly. Like, for example, NASA will have their interim and final like reports on a 6-month schedule. That's a little tight, honestly, for a lot of these things. It doesn't give you a lot of like leeway if something doesn't work well the first time around. It oftentimes it's not about the budget. It's basically about the timing to basically get it scheduled, because oftentimes the test they're looking for is not necessarily something that you can do in-house. It's you got to pike this into a university or an external lab or something like that. I've seen that plenty of times. But like a lot of these agencies, they're looking for monthly reports, especially if they're not NASA. I've seen basically a couple of DoD ones where they did want like a monthly reporting schedule, and namely I think DARPA had it that way. So I whatever you want. It's basically, we either spend time on this now or spend more time on it in one big block later. And it's probably to be honest, it's probably better to have more monthly reports in a lot of ways, just to basically keep everyone like connected. But that's a lot more paperwork too, on everyone's end. So like, I mean, what's best is like, I'm not exactly sure, but I've seen a lot of that. And like for like, NASA has a lot of ways, like the most like orderly process I've seen in a lot of ways, in terms of like, okay, so everyone that gets a phase 1 finishes on such and such day, right? And that is fine with us, right? Like for most of the DoD ones, you can put a couple into the same center basically, and they still come out on different days. Like you do see that too. I mean, that happened to us. So it all depends. NASA has more technology reporting requirements as compared to, I think, some of the DoD ones. Like you're still required to do a lot of reporting with all of these, and so you'll definitely get your technical writing proficiency, and how well are you able to basically put down some pretty efficient text, basically to express yourself in as little time invested as you can. Not little time invested, but you know what I mean, like basically efficiently.
Right. You don't want to be stuck in reporting forever.
Yeah, exactly.
Okay, Jacob. So you're about to invent this glue substance, and you have to commercialize it if it's going to be a winner, right?
Yeah.
How do you go about finding out who target customer, terrestrial customer might be?
Well, actually, as it turns out, there isn't a lot of different high temperature adhesive options, and there's certainly none that work quite like ours. So, and what I mean by that is basically, what we were looking for in terms of like looking for customers was, is there a user set, right, that needs basically like high temperature performance, right, and doesn't want to basically, for example, use like a fastener, right, like a traditional fastener. They don't want to like, or they don't want to use like a weld, like because they're trying to move away from like basically like metal structures, and start and use composites to start lightweighting things. There's a lot of different users of a performance polymer these days called PEEK, right? And we offer basically a way to bond the entire PEEK family, which are called the aryl ether ketones. To bond those at temperatures that are less than the melting point of PEEK, right? Because the typical way that you would have to basically bond PEEK is you would have to melt it, and a lot of times basically that's bad for your structure. So that's one of the features. We want to be able to use it with other people's high temperature composites, right? Because that is actually also a expanding field, just because as more people want to lightweight stuff, and they're putting things at hotter and hotter locations, not just in aerospace, but like in automotive, we want to basically make sure that that fits well. There's also a lot of different appliance applications, actually, as it turns out, that are relevant for that, that we're in touch with. And then as we move further down the performance chain, we also look at electronics, but also up on the performance chain is also electronics, actually. So there's actually a lot of different terrestrial applications for that. And for ATSP, the actual company, the main thing we make is basically the two-part system that goes to this, right? It's a lot like epoxy. It works as a two-part system, and we take that two-part system and we sell it for wear-resistant coatings, for friction and wear applications, for foams, for composite, for basically everything that people typically use polymers for. And we've learned how to work a lot of this stuff. So all of those combined actually ends up being quite a lot of different irons in the fire. And so it's really about trying to figure out which of these to actually focus on at any given time. And a lot of that's basically inbound driven from customers looking for, they'll see basically us in a peer-reviewed literature or trade literature, or they'll do a Google search. Basically a Google search, right? And they'll be looking for something that they don't currently have, and that includes our adhesives, but it also includes all of our other products too. It happens a lot, and so a lot of our contacts are actually based on more or less people's Google searches, more or less them reading articles. So it's mostly inbound. We don't do that much outbound, because we happen to know that we have a niche that is not filled right now, right? And as well, it's it's just about the budget of going outbound.
Okay. What about at economic order cost of making this stuff? When you're in the experiment, when you're in the SBIR phase, it doesn't really matter, right? You're going to make a little bit of it, and it can cost way too much, but you're proving the concept, right? When it becomes a commercial product, now you've got to make a vat of it, and you've got to make it at an economical level. Did you have any challenges doing that, or was that a pretty easy transition?
It was mostly about finding enough. In a technical sense, a lot of that is actually quite challenging. It is always a challenge, basically, to scale up. And there was a lot of technical challenges that we had to adapt to, because when this technology was basically handed to me back when I was in grad school, the actual synthetic route of it worked quite different than what we do today. We still make the same stuff, basically, but I had to basically take it and kind of rearrange some parts, I'll put it that way, to make it all be cheap to make. Right. And that was in a lot of ways basically just the little Lego blocks that the chemistry is made of, basically. I don't mean it's basically the little building blocks that the chemistry is made of. It's the selection of those. It's the selection of when you do some of these steps, and it's tricky. And so we think we've got a lot of good ways to approach this, in terms of making that two-part system. And we have a lot of good ways to approach this to make stuff downstream of that. And it's also, you know, a lot of it is for stuff downstream of that two-part system. It's about finding the right partners, right? It really is, because a lot of this gear is multi-million-dollar equipment that, you know, unless you have, you know, basically a venture or, you know, strategic partner backing you, that you're just not going to be able to afford, right? Like that to bring in house, right? So you find these partners. You have to basically find someone that has a round hole that's close enough to your square peg. You know what I mean? That you can kind of guide that through as best you can. That, you know, you can work with, and that's both in terms of, you know, the actual technology of it, but also sometimes, you know, a lot of these places, they don't want to work with you. You know what I mean? They have very little interest in working with a new vendor sometimes, you know, because they're like, oh no, like, I mean, this is how much you would need a year. It's not worth doing. You know what I mean? So you have to find someone that's at the right scale and, you know, like management in that entity that is interested in something new, which is not all of them, right? Like that's very far from it. So even basically finding, like, you know, like subcontractors and everything like that, you know, like it says always, they can say no too, right? So it is about like basically finding the right partners a lot of times, but it's also about just being clever with your chemistry and how you're putting things together. For us, that was some of our different scale up issues. You know, like it's you know, and for a materials company, there's a bit of chicken and egg action there too, right? So do you have enough orders to justify building this equipment? Okay, well, like, you know, you talk to some other like customer and they'll say, well, you don't have this equipment yet, so we're not gonna, you don't have this capacity yet, so we can't work with you. No, we're not going to buy it for you. Of course they're not, you know what I mean? So you end up with basically a little bit of chicken and egg action in terms of, do you have capacity first or do you have the customers first? And the way to circumvent that is basically to convince an investor to help you out there. But we're working on that aspect of things, but you know, like there's other aspects where we grew that organically, just by you know, our internal developments and you know, just customer traction. So, yeah.
Some good details there for people listening carefully from Jacob on what to look for and what to filter for. Don't just let his words wash over you. Go back and listen, because I grabbed a few good details out of what he just said.
Yeah.
All right, Jacob, let's finish up with this. Who do you want to hear from, connect with, and how should they, you know, connect up with you or find out more about ATSP?
Yeah, sure. So I would love to hear from anyone that is looking for basically like the more or less cutting edge of polymer science, right? In addition to basically the work that we do to make polymer right now, like that, the stuff that we make right now, we are also more than capable of pushing the boundaries on what is possible as far as polymers go. And we love doing that. And we love partnering with university faculty that have ideas along those lines. Right. I mean, we want to, like, not just basically customers. We also want to hear from partners that have an idea but aren't really sure where to go with it at this point. Right. We have a lot of different experience in that regard, and you know, we you know, love having collaborators. Other people have good ideas too, and we love helping all these things go from point A to point B, whether they came from our heads or not. Right.
All right. And where should they go?
They should go to the ATSP website and just basically like put in, like, go to our contact page, send us, and that'll just go to our, like, you know, our email inbox. So it'll get to us. Absolutely.
All right, Jacob. Appreciate you doing this. Yeah. So go ahead.
Or reach out on LinkedIn or any
Always
other
good.
sort of stuff like that. Yeah.
Okay. All right. Thanks a lot.
All right. Super. All right, Jason, you have a nice day.
I appreciate Dr. Meyer joining us with his insights on developing commercial technology through the SBIR programs, which is not easy to do. Okay, I encourage you to go look at their website at atspinnovations.com, and that link will be in the description down below. Also, a reminder that Cold Star Technologies is a supporter of the Operational Excellence Society. I'm on the board of advisors. And check out the America's Future series if you're at all interested in supporting America. All right, if you're a defense or space business owner and you have a to-do list a mile long of important but not maybe super urgent things that you're not getting to, but if you did get to them, it would really transform the way you're doing business. We need to speak. Reach out to me through LinkedIn or coldstartech.com. You can book a time there as well to speak with me. Thanks.